Welcome to Chapter 8, Working with Chemistry. Last chapter, we looked at fuel and how we use this fuel to make energy that to be used in an engine and thus make work. Now, our body works very similar to this engine in that we are going to use food as a fuel source to power the engines of our body. Now, there's several different types of energy that we can talk about. The main types are potential energy and kinetic energy. Potential energy, of course, is the energy that is stored in an object or substance. Most often we think of this as in physics as the energy related to a location. Like we put an object really high up and stored a lot of potential energy so that when it falls, it releases that energy as kinetic. But we can also think of that as composition, like what it contains. Now, kinetic energy is just the energy of motion. The equation is 1/2 m mass times velocity squared. We won't really use that, but it's there. It's the energy of an object moving at a certain speed. All these are types of energy, which energy is simply the capacity to do work. So when we look at potential, it's, as I said, it's stored through position or composition. You could have a diver up on a diving board. The higher he climbs, the more energy he's storing. So when he jumps off the board, he releases that as kinetic energy. When he hits the water, he moves the water aside, which he turns that kinetic energy into work as he pierces the surface. But energy can be stored in nature as hydrocarbons, for example. We can store this potential energy as a chemical energy into hydrogen bonds, whether this be methane, gasoline, paraffin. We can ignite these to turn them from potential energy back into kinetic energy to move our car or to heat a lamp. The same way, food is converted from its potential energy in the body to produce heat or the action of the muscles or make our organs function, various other things. Now, energy can be biological, chemical, electrical, thermal, and even other besides that. But more often than not, we're going to imagine energy as just heat. It makes things a little bit easier. Now, sometimes ideas will get lost for a time. Even really good ideas will get supplanted by worse ideas for a while, only to eventually return with a vengeance. Just take Democritus and Plato. Democritus had the atomic theory, well, had his theory of atoms, and that got supplanted by Plato's 4 elements. Now, well, it's still kind of atomic in nature, but he imagined everything made out of 4 elements: the earth, the wind, the water, the fire. And it wasn't until Dalton came up and refreshed this theory of elements that suddenly we remember, oh yeah, someone had an idea way back when. Well, this happened with the theory of heat, starting with Francis Bacon. Bacon was born in 1561 in England. He was a statesman, an essayist, father of both inductive logic and the modern experimental science. But what is inductive logic? Inductive logic is different from deductive. Deductive says, I see this, so this must be the case. Inductive logic allows the conclusion follows from a following premise with some degree of probability. It allows for the conclusion to be false even if the premise is true. Now, just because I see something happening one time doesn't mean it's always the case. It allows for some degree of wiggle room. Well, in 1620, Bacon wrote that the heat results from motion. Essentially, heat comes from motion and nothing else. There's not really any other thing to think about. So atoms, as we'll see later, are bouncing around at certain speeds. Cold atoms bounce less. Hot atoms bounce more. And as they bounce into other atoms and transfer some of their bounciness, some of their motion to other atoms, and thus heat them up. So heat can spread out by spreading out motion within atoms. Well, Bacon died in March of 1626. He had a brilliant idea. Riding in a coach, he was struck with the sudden idea that cold be used to prevent the decay of meat. So immediately wanted to go out and test that. He bought a turkey and began to stuff it with snow. He would later die of pneumonia that he caught as a result, and thus ending his career prematurely before he created the modern refrigeration. Well, his theory was overwhelmed by what's called the caloric theory for close to 150 years. Caloric comes from the Latin word calor, which means heat. And this imaginary calor was a mysterious fluid that could flow from hot objects to cold objects and thus transferring between them. Now, a calor didn't have weight, but it did have volume, which is how they explained why a hot object and a cold object weighed the same, but a hot object and a cold object often didn't have the same volume. If you've ever seen ice is a lot less dense than water of the same weight. Metal will often expand as it's heated. So they imagine, well, this calor was flowing into it and giving it more volume. If you want to hear some other really stupid theories, look up the word phlogiston with, I think it's a PTH or PF something, but it's one of those like silent P's. The phlogiston theory of combustion was another one of those theories that held its sway for far too long. But so this theory was killed partially thanks to Benjamin Thompson, aka Count Rumford, in the middle. He was born in 1753 in Massachusetts, but he was a loyalist in the time of American Revolution, and so he moved to England after the British lost the war. So he would then go on to travel around Europe and eventually serving the Duke of Bavaria, where he got his title. So one of his jobs while working at Prince, the Duke, is that he was supervising the boring of cannon. So you take a solid chunk of metal and you hollow it out so to fill the cannonball. So you bore it with a strong drill. Now, this produces a metric butt ton of heat. There's a lot of heat that gets produced when it does this. Now, the prevailing theory is that once the cannon is bored, it produces a lot of fine metal shavings, and these metal shavings couldn't hold the calors as well as the solid metal, and so they would flow out of that metal shavings as heat, and so you feel that heat is the calors fleeing the metal shavings. Well, he had a experiment where he was grinding this cannon in water for 2.5 hours, and it brought the water to a boil. And in the process of grinding, it produced 269 grams of the metal shavings. So it showed how grinding this produced heat and this much weight. We then showed that the same amount of metal shavings as solid metal cannon would take the same amount of heat to raise them by 1 degree C. So saying that the powdered metal could hold a temperature just as easily as the solid metal cannon, and thus there is the idea that a calors had to leave the metal shavings was false. So in 1798, he presented his findings to the Royal Academy for Science, that heat is just a physical equivalent of work, that when the heat was produced by grinding, the friction of drilling the hole and nothing else. And so the caloric theory was no more. it left us with only two things to remember it by: the term calorie and kilocalorie. Where the calorie is simply the measurement of the amount of heat needed to raise the temperature of 1 gram of water by 1 degree C, 1 degree Celsius. So how much heat does it take to heat 1 gram of water 1 degree C? Well, a kilocalorie is simply 1,000 calories, because a kilometer is 1,000 meters. So, or you could look at a kilocalorie is the amount of heat needed to raise 1 kilogram of water by 1 degree C. Either way, it still holds true. Now, if we want to measure these temperatures, we will measure the heat to work equivalent using the terminology is this: we use calorimetry, is the measurement of heat flow throughout an object. We measure them with calorimeters. But for the most part, other than that, the theory of calor is lost to the mysteries of time. But still more work needs to be done to fully put this theory down. And it was James Prescott Joule, who lived from 1818 to 1889, who finally did that work. He proved that any amount of work is directly proportional to the heat it produced. He did this through demonstration and measurement. He demonstrated that you can produce heat through mechanical work, electrical work, and even chemical work to make this heat, and that the amount of heat was proportional to the work, independent of all other factors. Meaning, if you're doing friction, you rub your hands together, you produce heat. If I rubbed two pieces of cloth together with the same amount of friction, you would produce the same amount of heat. If I rub two newspapers together, it would still produce the same amount of heat. It's all about the friction, not the surface itself. And then he successfully measured the ratio of heat to work, how much heat could be produced by doing so much work. We're so pleased with him that we honored him with the unit of joule. The joule is simply the work done by 1 watt of electricity within 1 second time. It's equivalent to 4.2 joules are equivalent to 1 calorie. Calorie is specific for water. Joules are typically the scientific measurement that most people use to measure heat. But for the sake of this chapter, we'll measure this just in calories. But we can do some simple calculations, as you'll see right now. So since we're in the Christmas season, let's do a quick calculation. If I have a string of 100 lights that use 4.8 watts, how much calories of heat would it take to run them for a period of 8 hours? So we're going to turn 4 watts times 8 hours, and we're going to turn that into watts per second. So the first thing we need to do is to turn hours into seconds. So there is 60 minutes in 1 hour, and there's 60 seconds in 1 minute. And this would give us units of watt seconds. 1 joule is equal to a watt second. So real quick, let's calculate that. So 4.8 times 8 times 60 times 60 produces 138,240 joules. Well, there is 4.2 joules in 1 little c calorie, and then there is 1,000 calories in 1 kcal. So let's look at that. So how much energy in kcals does it take to run my lights for that period of time? It takes a mere, well, let's say 32.9 kcals to run these LED lights for 8 hours. Now, when we do chemical reactions, like take methane and combust it to CO2 and water, it produces heat, like 213 kilocalories worth of heat. If I take pentane and combust it, it produces 845 kilocalories in heat. We see kind of a little discrepancy right here. These values are calculated from the equal number of molecules of each atom. So we choose 6.02 times 10 to the 23rd atoms of each, of methane and pentane. This number is 1 mole. We will talk about what it means to be a mole a little bit later, but right now just know it's a special counting number like a dozen. So we take equal number of atoms of each, and we can calculate 1 mole produces 213 kcals and 845 kcals, respectively. Now, at first glance, this ratio of heat is not quite obvious. That if you look at the heat differential, you produce 4 times as much heat per molecule of pentane versus methane. But if you look at the number of atoms, there's 5 times as many carbon, but there's 3 times as many hydrogen. And if you just look at the pure number of atoms, there's 3.4 times the number of atoms. So what is this magical relationship that always gives it 4 times as much heat? That while we cannot directly see the quantitative relationship at this time, just know it does exist. Does it exist because chemical energy is stored within the types of chemical bonds. And so we can measure this by looking at how much energy is stored in the bonds of the products versus how much energy is stored in the bonds of the reactants. Now, if there's more energy is stored in the products than the reactants, we release that excess energy, well, as heat. So it gives us our first type of reaction. An exothermic reaction is a reaction that releases heat as it proceeds. The majority of all reactions that happen naturally are exothermic. Does that mean that's always the case? No, but a lot of reactions are. If there's more energy stored in the products than in the reactants, it must consume energy to go forward, and thus it becomes an endothermic, a reaction that absorbs heat as it proceeds. So the difference between the products and reactants will control how much energy is lost or gained. With that in mind, if we were to try to do the reverse reaction, instead of burning methane to produce CO2, we tried to take CO2 and water and put it back into methane and oxygen, it must consume the same 213 kcals as it produced, because we got to put that energy back into its storage. So moving back to the human engine metaphor, that looking at us as an engine, that we need food to use as fuel to do work, which gets us to our metabolism. The metabolism is the combination of all chemical reactions that will take place in any living organism. So how do we turn food into fuel? The law of conservation of energy still holds sway in that energy in must equal energy out plus energy stored. So if we eat more food than we if we eat more energy than we expend, excess energy must be stored as fat. So if we want to lose weight, we have to either eat less food or expend more energy. And so that it would be energy in plus energy stored would give us the energy out. So it would have to burn some of the fuel. Oftentimes when we look at these energy, we look at capital C calories, large calories, which kcal is simply equal to a large C calorie. I'm going to use kcal to prevent further confusion, but oftentimes when you see calories on the back of your food, they're looking at capital C calories, not little c calories. But okay. So when we use our energy, our usage falls into 3 basic categories. 1, it's exercise. 2, specific dynamic action, and 3, basal metabolism. Our exercise is everything that our muscles are doing, moving around on a daily basis. Me giving this talk right now requires exercise. Shivering to stay warm, that's exercise. Staying awake while you listen to this talk, that's exercise. You don't have to go to the gym to do exercise. You going to the gym will expend more energy, but just being around and being awake expends some amount of energy as exercise. Now, specific dynamic action is specifically digestion and metabolizing your food. So when you eat something, your specific dynamic action takes effect. Your tongue starts to salivate, your stomach starts churning up extra acid, you start dissolving the food and absorbing the nutrients into the body. And so just the act of digestion in a whole takes some amount of energy. Your small intestine is absorbing the nutrients, and your bowels are essentially dehydrating and getting them ready for waste disposal. All that takes a little bit of the energy you're seeking to produce, seeking to absorb. It's the equivalent of distilling our crude oil out, cracking it down, and then refining it into different isomers. So it takes a little bit of energy to boil those, separate them, and then crack them apart, and then make the best fuel. But it takes less energy than the amount of energy we get out of it when we refine it. So it's worthwhile. On a whole, the SDA absorbs 4% of your energy if you eat some fats, about 6% if you're eating carbs, and maybe 30% if you're eating proteins. So you don't get the most amount of energy when you eating proteins. You consume a lot of it. But however, measuring the amount of energy lost due to SDA is not a simple task that you can simply add up the different components, because there's very complex interactions that we're not going to worry about. Just know that approximately 10% of the energy you've eaten is being consumed in the digestion process. And the basal metabolism is essentially everything your body does to keep you alive, even if you're not moving. Keeping your lungs breathing, keeping your heart beating, keeping your brain thinking, your blood pumping, everything you don't really have control of, your kind of autonomous systems are all working. Keeping your organs, your liver digesting, your liver producing enzymes, your gallbladder is producing various bile and whatnot, things you can't really control. All that's your basal metabolism. So it's possible to calculate the basal metabolism by, I think it's measuring the energy consumption after a 12-hour fast of a resting person. So after 12 hours of fasting, essentially all specific dynamic action functions have shut off. And by keeping them resting, they're limiting as much exercise as they can, so they can just measure the straight up basal metabolism. And they get it down to like, you expend maybe about 1 kcal per hour per kilogram weight. So a fatter person takes a little bit more energy to keep them running than a skinnier person. But you can measure how much energy they need just to keep the basics going. Now, when you talk about a resting metabolism, you're talking about you're combining your specific dynamic action and basal metabolism together without cutting out the exercise. One thing also to note is your basal metabolism can change through distress. So you get stressed, whether it's illness or test coming up or you're pregnant or something like that, you might need more energy to make everything function properly. So all these things go into effect. Basically, the fuel for your body works like this. This is a little bit oversimplification, but something like sucrose, which is a carbohydrate, gets combusted in your body essentially down to CO2 and water and a bunch of energy. There's a lot more that goes into it. You break it into glucose, you store energy in ATP and all sorts of things. And that's outside the scope of this, but just know that essentially it works like a hydrocarbon. We're breaking down the carbon, hydrogen, and oxygen into CO2 and water that we're going to expel. Now, this kind of differs. Metabolism differs from simple combustion in that they're not the same. First, metabolism is slower than combustion, and it doesn't produce any light, and it doesn't produce the high temperatures that you would see in a standard combustion. You don't produce light and heat, which is one of the key products of combustion. And two, it takes place under much milder conditions. You don't need that spark to keep this burning. You don't need the high heat to keep this burning. It will go on its own when they're much simpler conditions. Now, when we talked about energy in can come from three major sources: fats and oils, carbohydrates, and proteins. Now, I will largely skip the chapters involving these because this is a lot of stuff you'd get in your basic biology class, maybe a little bit of biochemistry, but unfortunately, it's not something I really want to go into. I'd rather do something a little bit more fun. So we're going to leave off talking about fats, oils, carbohydrates, and proteins. Just know that fats are large hydrocarbon chains, usually with some sort of acidic group or an ester group. Carbohydrates are large six-membered cyclohexane rings with a bunch of alcohols off them and ethers connecting them together. And proteins are long chain hydrocarbons connected by amide linkages. If you look back at the intro to organic chemistry chapter, I mentioned all of those functional groups. But if you look there, the energy you get from burning fat is 9 kcals per gram, while carbohydrates and protein are 4 kcals per gram. And this is regardless of the food source and what other nutrients are present. So it doesn't matter whether I'm eating a fatty steak or a ho-ho or ding dong. The amount of fat in both gives me the same amount of energy. It doesn't matter the source of the fat. It only matters the fat. Whether it's butter or lard or just fat off the bacon, it's all the same. Doesn't matter if the protein is fish protein or pork or legumes like peanuts. Proteins are proteins. Now, fat has the highest energy density, which is why we often store all of our excess energy as fat. We can't really store the carbohydrates for later. We can't really store the proteins for later, but we do store all the excess energy as fat because it's the most energy per gram, easier to pull back out later. When we look at ethanol, like alcohol, or you drink it, that's actually, ethanol has a energy density of 7 kcals per gram. So it's actually closer to a fat when it comes to burning this than it is to a carbohydrate or a protein. But let's show some quick examples of how you would calculate the number of calories in various foods right now. Let's calculate the amount of energy in this granola bar that I have right here. Salt and sweet. Looking at the box, it says it contains 8 grams of fat, 21 grams of carbs, and 3 grams of protein. So when we calculate the energy, there is something like 9 kcals per gram and something like 4 kcals per gram and 4 kcals per gram. The protein would have 12 kcals. The carbohydrates would have 84 kcals, and my fat 9 times 8 would be what? 71. Well, 72 kcals. 72 kcals. Adding these guys together. Get something like 168 kcals worth of energy. Now, technically, my box says it's 160, and it's close enough because when it reports the 160, it's leaving out the last significant digit. So it's somewhere between 160 and 170. So I think 168 is a fair number. Let's grab one other item. How about these Townhouse crackers? Calculate the energy. They contain 5 grams of fat, 9 grams of carbohydrates, and it says less than 1 gram of protein. So we're going to make that assumption that it's approximately 0. See how well that works. But 9 times 4 and 5 times 9. Kcals per gram. Kcals per gram. 9 times 5 is 45. And 9 times 4 is 36. 36, but 45 is 70. Something like 81 kcals. And I'd say that's pretty close because the box says it should be 80 calories, big C calories, 80 kcals. Now, as we look at the amount of energy we use globally, we use close to something like 1.5 kcals times 10 to the 17th. 1.5 times 10 to the 17th kcals globally per year. It's only going up. Maybe not too much, but it's still going up. 10 to the 17th. 10 to the 17th. 10 to the 3rd, that's 1,000. 10 to the 6th, that's 1,000,000. 10 to the 9th, that's 1 billion. 10 to the 12th, that's 1 trillion. 10 to the 15th, that's a quadrillion. 150 quadrillion, something like that. Kcals worth of energy per year. But 85% of those comes from fossil fuel and biomass, but we still get some from hydroelectric, solar, and nuclear and energy and like geothermal, among other things. But in reality, all energy originates from the sun, one way or another. All energy originates from the sun. That, remember back, the sun is producing fusion, where it's fusing together hydrogen molecules to form helium. And it's producing energy that some fraction of which makes it to Earth as light, as ultraviolet radiation and infrared radiation. Our light produces what? The daylight, among other things. The ultraviolet radiation does several things, but in terms of us, we can't see it. So all it does to us is give us suntans, sunburns, and skin cancer. So it's not too good. That our ozone layer will actually protect us from that, from too much of that. And the infrared radiation is given off as heat. So it's helping warm our planet, among other things. So because it's warming the planet and providing light, it's going to cause water to evaporate and generate that water cycle. So the water evaporates and then comes down in other places as rain and snow, and thus can keep generating water that's going to keep tumbling downhill that we can run through hydroelectric dams. This water, this heat that's going to be changing the water moving around is also going to be generating weather. So the sun is also responsible for the wind that is going to produce the windmill energy. And of course, the sun is going to help with just straight up solar radiation that we can absorb that. Of course, sun's going to help plants grow. Without plants growing and dying, we don't have any biomass, and we don't have any other energy sources. We can't have fossil fuels if we don't have things dying way back in the past. So all this energy, even the sun is going to produce various, as suns die, they will produce various heavy elements like uranium that can be shot out and be responsible for the fossil fuel. So the sun essentially gives us everything. The plants are probably the most common users of the solar energy that we see. They're going to use the radiation in photosynthesis to convert water and CO2 into the plant structures, into various nutrients, and basically fuels and other things that make that plant possible to live. This is overly simplified again, but essentially 12 CO2, 11 water goes to, and solar energy, you can produce things like sucrose and some oxygen as a byproduct. Now, not all plants are going to be producing sucrose, but essentially you can be producing things like cellulose and lignin and all sorts of funny things. But essentially we take water and CO2 and we make hydrocarbons. Essentially, a plant takes radiant energy and converts it into chemical energy. It's essentially the reverse of metabolism, one way or another. And that's going to be producing things like biomass. Biomass is the total mass of all life, including its waste products, residues, and remains. So when we talk about burning biomass, biomass could simply be wood. You could take switchgrass, you can take some weed, cut it all down and burn that. You could take corn husks and burn that. You can turn ethanol into corn into biomass, because corn, you can produce ethanol. It's basically the mass of all things that are directly living and that we can use as a fuel source. And all this contributes to the carbon cycle. Carbon cycle is the cycle where carbon shuttles among Earth's various natural storage facilities for the elements and its compounds. Now, the carbon will move from one region to another, largely as carbon dioxide. So plants will be one of the key components of the carbon cycle. When we move carbon is essentially going to be moving from a source to a sink. The source is where it's produced. The sink is where it's stored. So we're putting it from one place into somewhere else. It's like like a bank vault for carbon. Some things that were a sink before can be a source depending on the situation. A plant is the most common carbon sink. That a plant's going to take the CO2 from the atmosphere and turn it into plant matter. The more plants you plant, the less CO2 you're going to have in the atmosphere because it's going to be absorbed. Now, you could also store CO2 in the water by essentially dissolving it in as carbonic acid. However, that CO2 can also be released from the water. And so it could be a sink or a source depending on temperature and solubility. So don't think that's a perfect way to solve this. Metabolism is often a source because in metabolism, you're going to be exhaling CO2. But of course, burning of all types of biomass and fossil fuels would be the most common source. So if you burn wood, that all that energy, all that carbon you stored in the plant matter is then going to be released back as CO2. So you can store it for a little while. The thing of it is, fossil fuels are only a source, not really a sink. When we burn fossil fuels, we are releasing large amounts of carbon without the added benefit of being able to store it again, because fossil fuels take millennia to produce. So if we didn't have fossil fuels, the amount of the source and sink would be relatively stable, because wood and plants can grow just as quickly as they can be cut down and burned. So we can keep things more or less stable. But fossil fuels, because there's not really a sink to put them back in, we're just producing more and more CO2 faster than we can store it. The actual formation process for fossil fuels is not really fully known. We don't really fully understand it. We know something has to die. It gets buried. There is some sort of incomplete decay. It's not fully decayed down. And over time, heat and pressure, we can eventually turn something, whether it's plankton or plants, into coal and crude oil, but we don't quite understand it fully because it's over a much longer time scale and thus harder to study. Well, all of this is going to contribute to the greenhouse effect. Greenhouse effect is the warming of the earth by solar heat trapped through the insulating effect of atmospheric gases. The basic idea in a greenhouse, you can grow hothouse plants up north by putting a greenhouse. The greenhouse allows light in, it gets absorbed, it becomes radiant heat, and the radiant heat becomes essentially trapped in the greenhouse, and it's harder for it to escape. And so it keeps the greenhouse hot even while the outside is cold. That essentially the light comes in, but the heat, because of insulation, can't come out. Well, when we have this, with greenhouse gases, we have that same situation with the earth. The greenhouse gases are atmospheric gases that contribute to this effect. And essentially what happens is light from the sun comes in through the greenhouse gases, hits the earth, produces radiant infrared heat, and that kind of gets trapped in the gas layer and keeps on bouncing down and warming things back up. The heat can't quite escape again. Some of the most common greenhouse gases are CO2, methane. Oftentimes you see methane as, cattle farming, but there's other sources. Ozone and nitrous oxide. Please note, ozone is not always bad. Ozone in the upper atmosphere is good, but ozone in the lower atmosphere is bad. Ozone will absorb the UV radiation and protect us from sunburns, but down closer to the ground, it actually is corrosive for our lungs and not good. Nitrous oxide. Now, please note that all greenhouse gases are not bad. Some are good, and a little of them are good, but too much, and we just have a spiraling cycle. That the average global temperature will increase as we add more greenhouse gases. And as more greenhouse gases are released, we heat things up, and then things melt, and things kind of have a tendency to spiral out of control if we're not careful. The book gives an example of Venus, Mars, and Earth. Venus is almost all greenhouse gases, and it's a hellscape with temperatures hot enough to melt lead on the surface. Mars has almost no atmosphere, and so it's wicked cold. But Earth, with its atmosphere and slight amounts of greenhouse gases, keeps us warm. If we had no CO2 on Earth, besides there being no plants, we would probably still freeze. When we don't have enough greenhouse gases on, the Earth gets a lot colder. But we can see that right now we are producing a lot of greenhouse gases thanks to things like the Industrial Revolution and all of our fun little industrialization. And it's hard to blame third world countries because they're just trying to bring up their standard of living. But the fact of the matter is America still uses a majority of that energy. And we need to try to do something. You can see the temperature started a lot colder and was cooling down. Now it's slowly picking up, which each year it's getting a little bit warmer. Maybe not regularly the same jump, but it's jumping up year after year on average, higher and higher heights. Now, each time it heats up, you get things like more of the polar ice caps melt. As they melt, it releases some more gases trapped in there, which can cause things to get even hotter. So we're going to have very hotter summers. We're going to have rising sea levels. Miami may be flooded. We get more extreme weather. All sorts of bad things start happening that we need to try to take out. So greenhouse gases, a little dangerous. We got to think about that. So our prompt today. We're going to start from the premise that global warming is real, and regardless of what you think, that humans are contributing to it. Even if it's just a slight bit, humans are contributing to global warming. So how would you approach this problem? How would you try to slow global warming? Do you want to treat the source? Do you want to try to find new carbon sinks? Do you want to make small actions that can be easily done on a local level? Or do you want to try to act globally make for big changes? Like have conferences be like Greta Thunberg? So think about that. Make me an argument, 150 words. Make me an argument of how would you like to approach this problem? How would you like to try to treat this issue? Okay, I'll see you for chapter 9.